Okay, hello to everyone again. I think Nick is already connected. You can turn on your camera. Okay, Nick, how are you?
Good. How are you?
Very good. Very good. We are still a couple of minutes. I just basically close the breakout room, so probably in a minute or so we'll come back to the main room, and we will proceed with the second section, and I will introduce you.
Okay.
So I got your presentation. I already upload, I think, all the presentation, all the lectures at the webs, at the driver folder, and I think I give to all of you the rights to download.
Leonel.
Okay, Enrico, I think you.
Estuve muy ocupado ahí en el chat room.
Yeah, I know. We came back because we are on time to continue with the second section. And if there are people that would like to have more conversation, we can always organize a call.
Acá es mañana, como sabes, ¿no?
Yeah, I know.
Entonces ahora viene Nick, hace 2 lecciones, Raster Image y Number and Brightness.
Yeah.
Y después vengo yo con la aplicación.
No.
No, eso es todavía lectura. Y después en la tarde, más tarde tengo aplicación.
Yeah.
La número 3.
Sí.
Okay. Sí, está bien. Yo estoy acá en casa, todo está bien.
Okay. So if we are all okay, I will.
Okay, so I will mute my system.
Perfect. So I will introduce now our next speaker, Dr. Per-Niklas Hede is project scientist at the Department of Pharmaceutical Science, University of California, Irvine. As well, he's a member of the Laboratory for Fluorescence Dynamics on the same university. Nick is an expert in advanced instrumentation. He has particular experience during the PhD and the postdoc in super resolution instrumentation, light sheet microscopy, and all the film-related and FCS-related techniques. In particular, I want to emphasize his really large experience as a microscopy builder. He was my teacher during my time there. Teach me all the details about how to put the things together and make the things work when nothing works. And it's for me really a privilege to have him today. He's a big collaborator, a big friend. And today, the first talk will be related to raster image correlation spectroscopy. We will have a little break. Maybe we can have one question, and then the talk of the NMB, and we will go on with the other lectures. So Nick, you can share your screen.
Thank you very much, Lionel, for the introduction.
I will give you an advice when 5 minutes left, if you don't mind.
Okay.
Great.
Can you see the screen?
Perfect.
Okay. Okay, so welcome everybody to this first day's afternoon session, I guess. And so this session will continue on the fluctuation methods to be able to measure dynamics of molecules such as proteins in solution or in cells. In the morning, there was a lecture about FCS, so how to get this molecule dynamics from a single point. And in the following lecture, I will show you how to do this with the laser scanning microscope. And we call this approach the raster image correlation spectroscopy, or RICS. So what are the benefits of RICS? Well, you can do it with a commercial laser scanning microscope. Can be single or 2-photon system. You can do it with either photon counting detection or analog detection. Analog detection, you have to be a little bit careful. If you have the chance to join the practical session on Friday, we'll show you a little bit in more detail what's going on there using real data. Then, if you're interested in doing measurements in cells, RICS is particularly advantageous because it provides an intrinsic method to separate out the immobile fraction. You can also distinguish diffusion from binding. I mean, yeah, it's not only the movement of molecule, there could also be binding and unbinding happening in your system you want to study. So how does it work? Well, the idea is that whenever you acquire an image in a laser scanning microscope, you do this by focusing light into a point and then detecting light from that single point with a high numerical aperture objective. That point is about 200-300 nanometers in diameter. And so to get an image, you take that point and you scan it across the region of interest you want to image. And during this time, collect the signal and bin it into pixel. And this is how the image is reconstructed on the machine. So let's say we start here at the origin, so the upper left corner, and then the laser beam, which again is focused into a point, will scan one line. After finishing that line, it will usually, you will reset, will jump back. But then instead of going back to the origin, going one pixel down, scanning the next line, going back 1 pixel down, scanning the next line, and so on. And then after the image is complete, you jump back from the origin and you're ready to take the next image. If you've ever taken laser scan images, you can typically see this process while it's acquiring. Scanning one line is too fast for you to see, but you can usually see how the image is built up line by line. Yeah, so how it's continuously going through. Okay, so this means our image already contains a time structure because each of those pixels were acquired sequentially after each other at different times, and we know which time because the pixel dwell time is one of the parameters we set in our instrument. From the pixel time, we get the line time, which is the time it takes to scan a line plus the retracing time going back to the origin. And then, of course, we have the time for one frame. So here on the right-hand side, you see an example of a cell expressing a fluorescent protein. And this is a raster scanned image. And now we know that some of the information, some of the fluorescent signal that is more on the top left of the image was acquired earlier than some of the information on the bottom right. So how can we exploit this time structure of the image to get some underlying information about the movement of the molecules? So consider we have a molecule at any point in solution or in space. We consider this the origin for now. And we put our laser spot where that molecule is. And now let's start a clock, which means the molecule, because it can diffuse, it will start moving, and the laser beam, because we're scanning, will also start to move. So our laser is now at point 1, scanning this pixel, getting fluorescence from the point 2, getting a signal from the molecule, but then we are scanning point 3, point 4. And because the molecule is moving slow, we will not get signal in pixel 3 and 4 from that particular molecule. So if we calculate the correlation, meaning how similar is the signal compared between pixel, then, well, between pixel 1 and 2, it's very similar because we are detecting signal from the same molecule. Whereas in this case, pixel 3 and 4, that molecule is no longer in that spot. So the signal is not very similar. So we will have low correlation amplitude. So this is what you can see on the right-hand side. So this is the correlation, spatial correlation from one pixel to the next pixel. And then we have this decay curve. And this is our slower diffusion. So we have high correlation for short pixel distances, and then very low correlation for long pixel distances because the molecule was not able to move very far. How does this look like if we have fast diffusion? So let's start again, have the molecule here at the origin on the left. We put our laser there, we start scanning. Now the molecule is moving much faster, which means that we have a chance to get signal from that molecule also in pixel 3, 4, 5, 6, 7, and so on.
Nick, sorry to interrupt you. I don't know if it's intended that you want to share what is your view, because we are also watching at what your annotation.
Oh.
And maybe you can stop sharing and then do it again, but
Yeah.
Sorry, I have to swap.
Okay, much better now.
Okay, good. Sorry about that.
No worries. Go ahead.
Okay. Okay. So in the case of the fast diffusion, we have a chance to be able to get signal from the same molecule also at longer pixel distances. And this is depicted here with the red curve. The spatial correlation for longer pixel distances in the case of faster diffusion is non-zero. You see this extension of the tail. And also in the beginning, it's reduced because the molecule, I was showing you here the particular case where the molecule will follow the motion of the laser beam. But of course, this is just a stochastic process. So the molecule can also move in a completely different direction, far away immediately from the laser. So this is why we have this decrease in the beginning. So decrease in the beginning and an increase towards longer distances. So what is the operation that we have to do on our images to get this kind of information? I already told you we have to calculate the correlation between pixel and for different pixel distances. So distance from pixel 1 to 2, pixel 2 to 3, pixel 3 to 4, and so on. Because any of those pixels could be an origin for a molecule starting some movement. So lots of combinations we have to take into account. So for example, we start with pixel shift equal to 1, correlate pixel 1 with pixel 2, 2 with pixel 3, and so on for that line. Then we have to go to the next line, do the same thing, 1 to 2, 2 to 3, and so on for the whole image, or at least for the whole region of interest that we want to analyze. Then we have to repeat the process for pixel distance 2, or pixel delay 2, then for pixel delay 3, and so on. Do everything again for the whole image. And then, of course, we also have can calculate the correlation between lines, not only between pixel, but also between line number 1 and 2, line number 2 and 3, and so on. And then we have all the combinations between pixels and lines. So quite a lot of calculations, you would think. How do we do this? Well, we take the image. So this is our laser scanned image, which is just a matrix of different pixels. In this case, it's 256 by 256, but can be other sizes as well. So then we duplicate this image, but then we shift the image according to the pixel shift or line shift or combination of the two that we want to calculate. And then we just do the multiplication operation, and then we have to also normalize by the average intensity of the image. Yeah, so we shift this duplicated image in X and Y directions, and then repeat this for all possible pixel and line shift combinations. Then another thing we typically do in those RIX experiments is that we don't only acquire one image. Usually we acquire more than one image. For example, this can be 100 images. And there are two reasons for that. Mainly, one is to, of course, get a better signal to noise. We have 100 instead of just one image. We will have much improved statistics. But also that we can use this image sequence, as you'll see later in this presentation, to do some corrections, to remove the immobile fraction, to remove slowly moving components. So in any case, we take each of those frames, calculate the spatial correlation, and then we average all of them to one final 2D correlation image, which looks typically something like this. It's kind of peak in the center, typically. Okay, so how do we now analyze the data? How do we extract the information from this correlation curve? Well, in the raster scanned image, as you've seen, the points are measured at different positions and also at different times as the laser beam is moving along. We consider the pixel sequence is continuous. We just scan along with the laser. The time sequence you see is at some point we will jump back to the next line. So we have to take into account how this image is exactly made up, depending on the scanning motion. So in the RIX approach, we calculate the 2D spatial correlation function. And this is shown here. Here you see the RIX, the formula. And if you remember the FCS lecture, it looks actually very similar. So we have the intensity, fluorescence intensity, and in the FCS you had it as a function of time, and then you multiplied it with the intensity as a function of time, but t plus tau, so at a time delay. So now instead of this time delay, we have a pixel delay, which intrinsically contains a time delay. But so we have a pixel as a function of x, y in our image, and then we multiply it with pixel x, y, but with a pixel shift and with our line shift. And then we normalize the whole thing with the average intensity squared, and then you can subtract 1. So these pixel and line shifts are those spatial increments in x and y directions from a laser scanned image. You might think, oh, these are a lot of calculations, so maybe this will take a long time. But actually, you can use fast Fourier transform methods to calculate this very efficiently. Again, in the practical session, you will see it will only take a second or so to do the calculation for the entire image. So in this RIX analysis, we must account for the relationship between time, position of the laser scanning beam. So let's take a closer look at what parameters this correlation function contains. Well, we can split it up in two terms we call S, which corresponds to the scanning motion of the laser. And this is independent of the molecule dynamics that's going on. Here, the laser scanning is not supposed to influence the molecular dynamics, and the dynamics is not supposed to influence the scanning motion. And then we have the remaining term, the G, which now similar to the FCS contains the information about our moving molecules, which could, for example, be diffusion. In the case of diffusion, we can describe the probability function to find a molecule at a certain distance at a certain time. Here's this, it's an exponential decay. So we have here the normalization in the beginning, 1/4 pi dt to the power of 3/2. D is the diffusion coefficient. And then we have the exponential term here, minus r² for dt. Again, D is the diffusion coefficient of our molecule. So if you have a fast moving molecule, consider we put all our molecules at a certain point in space, and then we start the time so they can diffuse. So this probability function will go down in the center, but spread out in all directions as the molecules can diffuse out. And the speed at which this happens, the spreading, will make a difference if we have faster or slower diffusion. So from the kind of decay of this function, we can get how fast our motion, in this case, the diffusional motion is. How is this expressed in math? So at any position, pixel shift, line shift, the autocorrelation function in the case of three-dimensional diffusion takes this form, which is essentially the same as the FCS formula. So you have this normalization here, gamma over n. N is the average number of molecules we find in our observation volume. Then we have the 4D. In FCS, you would have the tau, the time delay. Now we have pixel dwell time with pixel shift and line dwell time with line shift. So just replace this with that. And then here we have the size of our observation volume squared. Because it's 3D diffusion, we have the second term here. Again, instead of just tau, now we have tau pixel, pixel shift plus tau line, line shift. Okay, this describes the motion of the molecule. Then we also have to have the function that describes this motion of the laser beam of the scanning, which is just an exponential decay. And the parameters here, again, we have pixel shift, line shift, and then we have the pixel size, delta R. And again, the diffusion coefficient will play a role. So if you would consider a situation where the diffusion coefficient is 0, so no motion at all, just particles sitting there, this spatial autocorrelation function will give you the correlation of the point spread function. Consider if you, in these equations, if you set d to 0 everywhere, we just end up with this pre-exponential factor gamma over n. And then this will also, this term will go to 0. So then we just have the representative of the point spread function of our instrument. As the diffusion increases, so becoming larger than 0, this correlation G term will become narrower and the width of the S term also increases. This is demonstrated here using a simulation. So we simulated molecules, fluorescent molecules moving at different rates, diffusion rates. On the top, we have very slow motion, so 0.1 micron square per second. This is the laser scanned image of the simulated data. Then if we calculate the 2D spatial correlation, you will see we get this peak, and it's just round. It more or less just represents the point spread function of the individual particles because they are moving so slowly. We barely see any deformation of the function. in the middle row, we have a simulation of 5 micron squares per second, which could be something like 14 nanometer beads diffusing in water. So now you can see as we scan while the particles are moving, we get these kind of distortions in those lines from the motion. So if we analyze this, you will see that the correlation function now is deformed. So it's compressed between lines, and it's elongated along one line, which makes sense because as the particle is moving, we have a higher chance to find it again in the same line, but then at later pixels in the same line. But as we jump to the next line, which will take a longer time, there's a chance that the particle has moved away. Here's the pseudo 3D representation. Then on the bottom, we have the fast diffusion, could be, for example, a green fluorescent protein in water solution, about 90 micron square per second. And now these distortions from the motion in the laser scanned image become very pronounced. And if you look closely, you can see that often you only have a streak in one line and then not again in the next line, because by the time you go to the next line, the molecule has moved away completely. So in the spatial correlation, we get this extreme compression now. So we have very elongated correlation from one pixel to the next in the same line, but then not much at all between lines, because most of the time the molecule has moved away by the time we get to the next line. Okay, let's look at sections, horizontal and vertical sections of this 2D correlation functions with a simulation of different diffusion coefficients. So on the left, we have the pixel-to-pixel correlation. We simulated different diffusion coefficients, 100, 10, 1, and 0.1 micron square per second. Now, if you, in the black line, the fastest, the 100, you see we have this reduction of the correlation in the beginning, and then this increase extension towards longer pixel shifts. Then this is reduced as you go to slower diffusions. And in the case of 1 and 0.1, there's not much change anymore because it's already relatively slow. So basically, the pixel-to-pixel correlation is very sensitive for fast diffusing molecules, but not very sensitive for slow-moving molecules. Let's look at the line-to-line diffusion case. Here it's the opposite. At very fast rates, it's very unlikely we will be able to capture the molecule in the next line. So we start basically with almost 0 here. For the fast diffusion, 110 micron square per second, so not much sensitivity here. But then in the line-to-line, we have high sensitivity for the slower moving molecules because it takes them longer to go to the next line. How should you set up your laser scanning microscope? In general, the faster the molecules of interest are moving, the faster you need to scan to be able to follow their motion. Here are just some very general numbers. Of course, it will also depend on the instrument you're using, and you probably have to tweak it a little bit. In the beginning, in your experiment, I mean, you want to find out the diffusion coefficient, so you probably don't know exactly, so you maybe have to do a couple of tries with different scan speeds to see which fits your experiment the best. In terms of pixel size, so what is the zoom that we want to select on the laser scanning microscope? In general, it should be smaller than the point spread function. And the reason is we need to be able to capture this decay to be able to apply our fitting. I'll show you on the next slide what happens if you don't do that. Molecular concentrations, we have the same limitations as conventional FCS methods, meaning that in general, those methods work better if you have lower concentrations. The argument is that if you have 10 molecules on average in your observation volume, one moves in, one moves out, you have 10% fluctuation of your signal. If you have 100 molecules, one moves in, one moves out, you have only 1% modulation of your signal. So this is kind of the hand-waving argument. It turns out that it's actually, theoretically, if you increase the number of molecules, because the signal increases as well, you would expect the same signal to noise, so nothing should change. However, in the real world, you have other fluctuations. For example, from your laser, the power can fluctuate a little bit. You can have fluctuations from the electronics in your detector. And as you go to higher concentrations, then these will dominate your measurement. And this is the reason why generally those methods work better with lower concentrations. Okay, so here are two examples if your instrument is not set up correctly. In the top, we have a case where we have fast diffusion, like a dye molecule in solution, but we have very slow scanning. You see, we have this very long tail. We are not able to catch the molecule as it very quickly moves along. So we have this, we're missing some part here of the correlation. In the bottom part, we have the case where we selected our pixel size too large. In this case, it was set to the size of the point slit function, 0.3 microns. And then you see we just have the strong correlation from the center, but then because now the distance is very large, we basically jump and we are not able to capture the information here. So our fitting will not work. This is why you should select a pixel size that is a couple of times, 3 to 5 times smaller than the point slit function. Okay, let's go to some real data. Here's green fluorescent protein solution. This is a raster scanned image, one image. Here's the spatial autocorrelation function. And just as in the simulations, you can see that we have strong pixel-to-pixel correlation, but almost no line-to-line correlation, indicating that the molecule is moving very fast. Applying the fit, we get this 100 square micron per second, which is the value we would expect for EGFP in aqueous solution. Then another question to investigate is how many frames should I take? What kind of frame sizes should I choose? Yeah, it depends, of course, also a lot on your sample. On the top, we have the G0, so the correlation amplitude, which is relatively robust for 256. And then the different bins are different number of frames, from 500 frames to just looking at 1 frame. So you see it's almost all the same, very robust. Then we go down in the region of interest to 128, 64, 32. Except for maybe 32, this is a pretty robust measurement. Now let's go to the diffusion coefficient, which is usually what you're interested in. Different regions of interest, 256 by 256, again down to 32 by 32. And then if we combine 100 frames, we get very good statistics for both 256, 128, and then a little bit worse for 64. But then not only does our error increase, we also suddenly end up with a slower diffusion coefficient than we should. And this is consistent here for all the different simulations, 100 frames, 50 frames, 10 frames, 5 frames. And the reason is, as we make the region of interest very small, we are not able to capture the full decay of the function. And as we cut it, we will underestimate our diffusion coefficient. So this is something to keep in mind if you do analysis. Often in cells, you want to look at small regions of interest to get more detail. But if you have fast moving molecules, be aware that to not underestimate the diffusion coefficient. Okay, what about the concentration? Similar to FCS, you can also measure the number of molecules, and if you calibrate your PSF, you can get the concentration from RIGS as well. Here is just shown the result from RIGS versus the absorbance measurement, and you can see it matches very nicely, a perfect linear relationship. So this works well. What about cells now? Because if you have a solution, you might as well do single point FCS because the solution is supposed to be the same everywhere. So what about cells? In cells, we have an immobile fraction. The 2D spatial correlation of an image that has immobile features has a very strong correlation pattern. And we need to separate this immobile fraction out before we can get the information about the dynamics of the molecules. So how can we do this? Well, first, one question is, does the noise from the detector correlate, which would be bad. If you have a truly immobile bright region, the intensity fluctuates according to Poisson statistics due to shot noise. And the time correlation of shot noise is 0, except at the 0 time point or 0 pixel delay, which we will not consider for the analysis. The spatial correlation of intensity at any 2 pixels, so due to shot noise, is 0, even if the 2 points are within the point spread function. And if we subtract the average intensity and disregard the 0 point, the immobile fraction totally disappears from the correlation function. There could be some issue if you're working with an analog detection, depending on the electronics. Those have some kind of filter effect that could lead to a little bit of a correlation between neighboring pixels, which you have to account for. You will also get more information on that in the practical session on Friday. Okay, so how do we subtract this background? Well, we calculate the average intensity of each pixel of the overall stack. Remember, we acquired not only 1 frame, but maybe 100 frames. Then this average intensity in each pixel, we subtract from the individual pixels in the individual frames. However, this could potentially give negative values, so we add back the total intensity, the total average intensity to compensate for that. And then after doing this calculation to the data, we correlate our correlation function and then end up with the spatial correlation that only contains the dynamics of the molecules and not any spatial features of the cell, for example, any shapes of the cell. When you go to the real experiment, you could have a case where some structures of the cell slowly move, or there could be bleaching. And to compensate for that, what we usually do is, instead of calculating the average over all the frames you acquired and subtracting that, we split up our image stack into window. So we have a sliding window where we calculate this average in, let's say, over maybe 10 frames and do our correction for those 10 frames and for the next 10 frames and so on to account for slowly moving features and also for changes in signal that could occur due to photobleaching. Here's an example of images where this operation was applied. So this was frame, just a single frame. Then we have this moving average window, which is the intensity you can see here. So that contains all the immobile features. We subtract that, add that back in that global average, and then this is the data you get, and this only contains information about the moving molecules. Yeah, here's an example: a cell expressing EGFP penicillin, which forms these focal adhesions. As they are assembled, they become static. So they give a strong spatial correlation, but after doing the moving average correction, we see we are left with this correlation function that only contains the information about the penicillin molecules that actually move. And we can do our fitting and get a diffusion coefficient of, in this case, around 7 micrometers square per second. What can you use this for, this raster image correlation method? One example, for example, is cell migration. I already mentioned the penicillin molecule, which is found in the focal adhesions as a part of the focal adhesion complex. And to get there, it first has to cross the cytoplasm. So if you see the cell, you see a lot of it in the cytoplasm, and then you have it accumulated in the focal adhesions. So here are some laser scanned images again of a cell expressing this EGFP penicillin. And we do our RIX analysis. Now, of course, we are interested, is there a difference in the diffusion between the cytoplasm, say, and a region closer to the membrane around the focal adhesions? Well, if we analyze the cytoplasm, we get about 10 microns square per second. But if we go to those adhesion structures, it's very different, very slow, 1 micron square per second, or in some regions even slower than that. Yeah, so what you can do now in the RIGs is you can, instead of just analyzing the whole image and averaging everything, you can split it up into smaller regions of interest and then do the calculation for all the regions of your image, and then you can end up with a map where you have both the average concentration of your molecule and the average diffusion coefficient. So this is very nice result. Again, keep in mind that unfortunately you cannot make these regions as small as you may like because of the limitations that you still need to be able to fit your correlation function. So in general, with diffraction limited microscopy, the resolution of these diffusion maps is limited to a couple of microns typically. However, as you may know, there's also new approaches, super resolution, where you can go below these limits that are generally the resolution of a microscope in XY is 200 nanometer and in Z is 500 nanometer. And one of these approaches for the raster scanning microscope is stimulated emission depletion, where you optically switch a molecule between a dark state and a bright fluorescent state. And in this case, the switching mechanism is stimulated emission. So this is the same process that's happening in a laser. So we get our molecule into excited state. Then if we just wait, it spontaneously emits a fluorescence photon, which you can characterize by the fluorescence lifetime, the time delay. But if you send another laser pulse, which is in the range of the emission peak, you can induce the emission of a fluorescence photon and so force the molecule back to the ground state. And this is our K-off process to switch it off. So how do we do this? We have our excitation spot laser, then we have a depletion laser, which forces the molecule immediately back to the ground state. And we give it this kind of donut shape. So there's zero intensity in the center and then high intensity in the periphery. In this way, we can force all those fluorophores immediately back to their ground state and only get spontaneously emitted fluorescence from the center. And thereby we can effectively shrink down our point split function size with increasing the depletion beam power. Yeah, this is just a typical setup. This is a regular confocal microscope with our pinhole here. We scan our sample, we get this confocal image. We apply our depletion beam, forcing those molecules in the periphery to the ground state, and you can see you can very much increase the resolution. This is the math the formula how the resolution is improved, which depends on the stat intensity and also the efficiency at which you can deplete the molecules. And you can get resolutions for typically a couple of tens of nanometers, maybe 50, 60, 70 nanometers or something. Here's just an image again of a confocal versus a stat image. Okay, so back to our raster image correlation method. Now we have the stat. So our effective point state function is smaller, which means we can use smaller pixels, which means we can make a diffusion map that has a better spatial resolution. The other benefit of stat is that, remember we said in the beginning, typically it's better if you have less molecules on average in your observation volume. Well, with the stat, we shrink the effective observation volume. So it also works better if you have higher concentrations. Yeah, as you can see here on the right, as we crank up the stat power, we increase the correlation amplitude because we have less, because the volume is smaller, so we have less molecules at a given point in time. Okay, this is diffusion in the bilayer, just to see that the stat is working. So as we increase or decrease our PSF, we have, of course, observed less particles. And also the time it takes the particles to cross the volume goes down, as expected. So now back to our cells. So this is a lipid, fluorescently labeled lipid in the plasma membrane of cells. This is the confocal image. And you can see we are very zoomed in. And if we are trying to analyze small regions of interest, we don't get good correlation. Yeah, because the region is too small, not enough signal to noise. But now we apply the stat. You can see, well, we have better resolution, so the image sharpens up. But more importantly, the correlation functions now also become much more defined, even in the small regions of interest. So you can potentially get a diffusion map with better spatial resolution. Okay, so to conclude, what is the raster image correlation method? We can learn about the diffusion, but could also be other process, binding, active transport, trapped diffusion in cells. Our time resolution is in the micro to millisecond time scale. We can build diffusion maps with a spatial resolution of a couple of microns, and we can study movement of proteins, and also protein interactions. With the stat modification, we can increase the spatial resolution of our diffusion map, and we can also potentially go up to higher concentrations. What I didn't discuss today is the image correlation methods. These are generally better for slowly moving processes like membrane interactions. But the last session today is a very novel version of kind of an image correlation method. It's a variant. It's called the 2D pair correlation function method used to analyze images. So you will also see that we can also do something with faster moving molecules there. In any case, with that, I want to thank everybody who has contributed to the talk and the data I've shown you just now. And do we have time for questions?
Thanks, Nick, very much for the nice presentation. We are more or less on time, but I think we are able to have one question, and then we can move to the next presentation, which is also yours. So I will use this time to give you some moment to drink some water or whatever you want.
Can I ask a question?
Yeah.
So you show at some point that as you make the field of view or the number of pixels, whatever, smaller and smaller, the value of the diffusion coefficient changes a lot. It is biased. Okay.
Yeah.
So, well, you have to go back a few.
Yeah, this
one.
So, that one, you show that if you have 32 by 32 region, the diffusion coefficient becomes a green light, which green at all size, and always is biased toward lower value.
Yeah.
Now, when you do stead rigs, do you have the same problem or not?
Well, eventually, yes, but we also because the resolution is higher, those pixels that we choose, the size is smaller. So basically,
you have a lot of pixels.
Or you have to have a lot of pixels, yeah.
But the origin of this effect is that simply the molecules get out of the field of view.
Yeah, exactly. So also if it also depends on the motion of the molecule. If it's moving slower, then you can analyze in smaller regions.
No, that's okay. That I understand. Because this is calculated for
this is
GFP.
This is free EGFPs, which is moving very fast. So in cells, you actually have a better chance.
Yeah.
To
Okay.
have smaller regions.
But the issue of using an arbitrary region to do rigs is defeated by this principle. So in general, you cannot use an arbitrary region. So if you have a very narrow filipodia or whatever, you cannot do rigs in that filipodia.
Yeah, it will be very difficult. Yeah.
Well, yeah, it's not difficult to do, but you bias the result.
Yeah, it will give you a wrong value, right?
Okay, so anyway, let other people to have questions if they have.
Yeah, I mean, if you're doing the analysis, you can look at your correlation function and you can see if it's truncated. And if it's truncated, you're going to make an error.
Yeah, of course, I understand that. But people are trying to use rigs in micro and nano channels, for example. Yeah. And that, of course, you cannot use rigs as an image. You can use line scan.
You can do if you just do line within a line. Yeah, line.
You can do, but not within an image.
Yep. This is right.
Okay, so anyway, I want to simply clarify this principle.
Nick, meanwhile you are changing the presentation for the NMB, I want to ask you if do you have more than one connection with the Zoom? I don't know, because we have during the presentation your talk a little bit broke. I'm not so sure. I voluntarily basically turn off your camera just to save some bandwidth, but I don't know.
I think it's you're at home, Nick.
I'm at home and I'm connected to the Ethernet from the university.
Okay.
Yeah, but this is what is make it slow. Okay. I don't think there's any other way to speed it up, but. So Natalia has a question in Spanish. Okay, Natalia, you can ask the question. Natalia, I cannot hear. No te escucho.
So, hola, ¿me escuchan?
Sí, Natalia.
Can you hear me?
Sí.
Yes, sorry. I'm not sure how to ask it in English, but what I was wondering is if you made this same analysis several times for getting the chance to see if every time you get the same results or not.
Te contesto en castellano.
Thank you.
Sí, estos análisis, como ves, tienen un bias y una barra de error. Si miras la figura que está ahora puesta,
claro.
La barra de error está hecha su repeticiones de muchas veces, de 10 veces. Pero el valor está bias, y está bias porque no puedes ir la función Higgs es como una campana, ¿no? Pero si tú no la mides toda la campana, no puedes ver a dónde baja. ¿Entiendes lo que quiero decir?
Sí, la barra de error que tienen esos gráficos es por haber hecho varias veces el mismo análisis, ¿no es cierto?
No, son simulaciones, repetición de las simulaciones.
Claro, muchas repeticiones, sí, sí.
Pero el bias se queda, no hay nada que hacerle. El bias se queda porque tienes una dimensión que es demasiado pequeña para el coeficiente de difusión. Tienes que ir muy lejos para poderlo medir bien, ¿no?
Ok. Gracias, Enrico.
Okay, so there is another question from Lisandro, but considering that we are on time, I will put you, Lisandro, in the breakout room so you can discuss with Nick during the breakout session.
Okay.
Are you allow the new presentation for the NMB? Okay, great. If you share, I think everything is ready to go.
Yeah, let me.
Oh, okay, you have again the same.
Yeah. Okay, there we go. Yeah, I have an external screen connected, and then it tries to do the other one.
Yeah, I noticed. Okay, great. Thank you. Go ahead.
Okay, so the next talk is about the number and brightness method. And we usually have those two lectures after each other because you can also do the analysis after each other. So you can do the number and brightness analysis typically on the same data that you acquired for RIGS, which is very nice. Before starting, I want to point out that some of the data is also acquired by Michelle Digman. Okay, so the number and brightness is about, well, you can measure the numbers for the concentration, which you can also get from the RIGS or from the FCS. But yeah, as the second word in this method, brightness describes, we can look at brightness and thereby get the aggregation state. If two fluorophores are moving together, they should on average have to double the brightness. So from the brightness, we can tell if they are moving together or not. And you can do this, of course, for proteins in cells or other molecules in cells, lipids in cells, which can be very powerful. Okay, so one thing you can do if asked, well, what is the concentration in a particular region in the cell? Of course, you can look at the intensity. Let me change this pointer here. So, for example, we are here in spot A and we get some kind of average counts per second, let's say 30,000. And then we go to another spot where we have a much higher intensity, whatever, 90,000. And then if we do a reference measurement with a solution, in this case of the green fluorescent protein, where we know the concentration and the count rate it gives, we can infer the concentrations in those regions of the cell. So in this case, region A, for example, would have 10 nanomolar and region B would have 30 nanomolar. And this accurately describes the number of molecules that you have in those regions. However, what this doesn't tell you is if those molecules, are they bound together or are they just accumulate in this region because they are contained in some larger structure or something. So we cannot really measure the aggregation state just by looking at the intensity this way. There are other methods you can do, which is, for example, first resonance energy transfer or FRET, where you have two fluorophores, and they can, if they're close together, there can be energy transfer between the two, either a homofret if it's the same molecule, or if you have a donor and an acceptor molecule, you have transfer from the donor to the acceptor. That only happens if those two molecules are very close, within a nanometer or so. And then you can conclude that the two proteins that those fluorophores are attached to are bound together. So this is a very sensitive method and very nice method, but I'm not going to talk about it today. It's very sensitive to the formation of pairs. But what about other, for example, higher states of aggregation? Another method you would be able to look at that is image correlation spectroscopy. Of course, if you have very large aggregates, this will give you an increase in the size of your spatial correlation, and you can get the aggregation state from that. But that typically only works if molecules are moving slow and if they're relatively large. Okay, so what can the number and brightness method do for you? So it can provide you with a pixel resolution map of molecular, the number, so concentration, and the aggregation state of the molecule of interest in cells. How does it do this? Well, we look at the first and second moments of the fluorescence intensity distribution at each pixel. So this means we need to have more than one image. Another reason, when you acquire the laser scanning image, yeah, we have to accumulate 100 or even more images than that. What are the typical source images? We can have raster scanned images like from the RIGS experiment, but for the number and brightness, we can also have camera images from like a total internal reflection microscope or a light sheet microscope that were acquired with fast cameras. Because here we don't need a time structure within the same image as for the RIGS. We just look at the statistics in one pixel from one frame to the next. So here we can also use camera images. What do we get? We get the number and brightness maps. So pixel resolution map, and you get the 2D histogram of the brightness versus intensity, which can show you if you have these aggregations, you can select, for example, only dimers from that and then map it back to your image to show you where they are in the cell. You'll see an example later. So you have this kind of cursor selection method, which is very convenient, used in a lot of things. Also, I think during this week you will hear about the lifetime and the phases. So that's very nice where you have those two plots where you can select a certain property and then show you where it is on the image. If you do the measurement, you need to take into account what kind of detectors you are using, and I'll explain that to you in the following. And again, on Friday in the practical session, we're also going to look at NMB data and how you have to correct for your detectors. Yeah, and we'll show you how to get the data in and analyze some example data. Okay, so the question is, how do we distinguish pixels that have many dim molecules from pixels that have fewer but very bright molecules? Because this can potentially give you the same intensity. Many dim molecules can give you the same intensity as few bright molecules. So if we look at the average, and we have few bright molecules, in this case, for example, we have an average count rate of 19,000 counts per second. Here we have on the right-hand side, we have many but dim molecules, and we can have exactly the same intensity. So the average in this case would be the same. However, if you look at the variance, this describes what is the variation band of our signal. And of course, if these are moving, So we are always considering that the molecules are moving around. The intensity that you measure in that pixel will jump more if you have less but brighter molecules. So the fluctuations are larger. So this is described in this plot here. So the variation of your count rate is much higher for brighter molecules than if you have the dimmer molecule. So here we can already make a distinction. So given two series of equal average, the larger is the variance, the less molecules contribute to this average. And the ratio of the square of the average intensity to the variance is proportional to the number of particles. So this is again how we can get the number of particles or the concentration in our region of interest. So how do we calculate these protein aggregations or measure protein aggregations from those images? So of course, in each pixel, we can calculate the average. So sum of intensity values in each pixel divided by the cumulative of all of them. And then we can also get the variance in each pixels. Typically, the units of brightness are, well, they are related to the instrument parameters, which is pixel dwell time, laser power, PMT gain, and all these settings, which you also have to take into account when you're setting up the experiments. And usually the unit, the intensity is counted at as counts per dwell time per molecule. Okay, so our brightness is defined as the average intensity per the average number of molecules. If you have less molecules and the intensity is high, you have high brightness. If you have low average intensity but a lot of molecules, you have a low average brightness. And in the brightness, in terms of the first and second moment that we calculated, is given by the variance divided by the average intensity for each pixel. And we can also rearrange this formula to get the average number of molecules as the average intensity squared divided by the variance. So these are the parameters that we have: variance, average counts, apparent number of molecules, and apparent molecular brightness, capital B, and the number of frames that we analyzed. Okay, so one question could be, how do I set up the instrument? We already said usually the data you get from RIGS is pretty well suited for number and brightness analysis. But if you're not doing RIGS, what should I look out for? Well, again, we get these we get the information about the aggregation state, assuming that our molecules will be able to move while we're doing the measurement, which gives us these intensity fluctuations in each pixel where we can apply our statistics to. So this means we have to have a dwell time that is short compared to the motion of the molecule. So we are able to see the fluctuations. So this is illustrated by the correlation function here. If we are measuring short dwell times, we are able to see the fluctuations. So we have a non-zero correlation amplitude. But if we are too slow, if we average too much, we will not be able to measure these fluctuations. So in this case, the correlation function is 0. So this is something to look out for. General, for the raster scan, we don't have much of a problem because the pixel dwell times are typically always in the microsecond, couple of microseconds, maybe tens of microseconds. So we are fast enough for diffusional motion in cells and tissues. But if you use a camera, you have to be careful to not make your frame exposure time too long. What you can do there is use some kind of stroboscopic illumination. So even you expose longer, you just give a flash of light, very short, maybe 100 microsecond or something, and then yeah, you will also again be able to see those fluctuations. So this is important if you are trying to do number and brightness on your camera-based microscope, like your TURF instrument or light sheet or something else. Okay, so what is the variance that we see? Well, we have a variance due to the particle number fluctuations. So the particles move, and this makes the signal fluctuate. And this is equal to the brightness of the particle squared times the number of particles that we have in that observed volume. But then we also have a variance due to detector shot noise. I mean, you probably have seen if you take, even you have a perfectly static sample like a calibration slide or something, you will still see variance in the signal, which is just the shot noise from your detector. And this is, in the case of the number and brightness measurement, this is brightness times number. So the measured variance contains these two terms, the variance due to the particle number fluctuation and the variance due to the counting statistics. So our variance consists of those two terms. And they have different dependence on the molecular brightness. One is dependent to the true brightness squared and the other is not. This is for the photon counting detector, by the way. So the ideal case for the analog detection, you have to do some more corrections, account for more things. You'll see in a bit. So both the parameters depend on the intrinsic brightness and also the number of molecules. So back to our brightness formula, this was defined as the variance divided by the average. Then the variance we just determined is made up of the molecule number fluctuations and the detector fluctuations. We can insert those formulas from the previous slide. And then for the detector, if it's like photon counting, then it's a perfect, it's a Poissonian distribution. And the property of the Poissonian is that the variance is equal to the average. So this term just becomes 1. Here, the epsilon goes out, the number of molecules goes out. So our apparent brightness is the true brightness of our molecule plus 1. This is important. So basically, if you do a measurement of something immobile, like a calibration slide or something, and you do the analysis, you should be getting an apparent brightness of 1. Because, yeah, the true brightness, there are no moving molecules, so this term would be 0, so you should be expecting 1. This is a good way to, if you're doing the measurement, it's a good way to test if your calibration is correct. If you have a measurement of something immobile, you should get 1. Okay, and then you can rearrange the formula to get the true number of molecules n and the true molecular brightness. So that would, for example, correspond to a monomer. And then from that, a dimer should have double the true brightness, a tetramer, quadruple the apparent brightness, and so on and so forth. If you calculate it this way, so directly to the true number and true brightness, however, there can be a problem if you go to regions where particles are immobile, because then we don't have particle number fluctuations, so we don't have a true number. You can see that if you're going to a Poisson, this term will become 0, so you will not be able to reliably do this calculation. So we usually use these in our plots, the apparent number and the apparent brightness, so capital N, capital E. Okay, as you've seen earlier, we have this quadratic dependence on the brightness of the variance on the particle brightness. Here is an experimental verification. So this was a 20 nanomolar EGFP solution. And to increase the brightness, you can also just increase the laser power. which in terms tells you to not change the laser power while you're doing the measurement. Yeah, otherwise you're changing the brightness of what you measure. But here we're doing it on purpose just to check, and you see we get this quadratic behavior in the increase of the in the variance as a function of the intensity that we would expect. Again, this was done using photon counting detectors. Okay, so some more evaluation of what you expect in the measurement and what's the difference between mobile and immobile molecules. As pointed out, the immobile molecules will not give you number fluctuations, and we also get an apparent brightness of 1, independent how bright our sample is. For the mobile, this will be different. So here on the right-hand side, we have our apparent brightness as measured. And then here we use the constant laser power, but increased the concentration for an EGFP solution. These are the red dots that you can see here. And you see that the brightness is larger than 1, which is good. As we increase the concentration, you see the count rate increases, but the brightness will stay the same because, yeah, we did not change the laser power. We only get more signal because we have more molecules, but the brightness of the molecules is the same. And we get this result. We get what we expected. If you push more, you see that at some point the brightness drops off. At this point, you see we're in the region of more than 1 million counts per second. So at some point you will start to saturate your detector, get in the nonlinear range. So you have to make sure to avoid this range. For photomultiplier detectors, the maximum count rate you can usually get is maybe 10 million counts per second, but at that point you're already in the close to saturation, so you should avoid that. Typically, stay below maybe 1 million counts per second or something like that. Again, it depends very much on your detector. If you use an avalanche photodiode detector, these have much lower saturation rates, so there you have to be even more careful. Maybe you can only have a couple of 100,000 counts per second. Also in the plot here is shown you a slide where dye is immobilized just in plastic, so the molecules don't move around. So we have this apparent brightness of 1, which we expect for an immobile fraction. And as you can see, in this case, we cannot change the concentration, but we can change the laser power to make it, to have more intensity, more counts. And again, you can see it does not change until you hit this kind of saturation here. Okay, so how about something a more real sample, or more complicated sample, I should say. The other one is still real. So here's a measurement of fluorescent beads immobilized on a glass surface, but there's also added 100 nanomolar fluorescein dye solution on top. So this is the intensity that image that you get. Here you see these beads, immobile aggregates, and also some intensity from the fluorescein, but this is much lower, much less intense than the beads. If you calculate the brightness map, you see that it's kind of inverse, because in the calculation, the immobile fraction has a brightness of 1. So these are these bluish color codes here where the beads are. And then from the molecules that can move, you have the additional component from the fluctuations from the movement. So we have this higher apparent brightness here. Here we have it quantified. So this is our plot of the apparent brightness as a function of the intensity for every pixel. So this is a 2D histogram containing all the pixels of this image here. So if we want to select the fluorescein, we select a pixel that have brightnesses larger than 1, because this is the addition from the number fluctuations. And if we do so, you see we highlight this portion of the image where we have the fluorescein. If we select all the pixels that have a brightness value of around 1, you see you highlight the immobile fraction, which in our case are the beads. Here is a series of different aggregates from monomer to octamer. Again, if it would be immobile, you would be expecting 1. Then the monomer has apparent brightness a little bit more than 1. And then the dimer has double of that. The tetramer 4 times of the monomer, octamer 8 times of the monomer, as you would expect. Okay, here are some more control measurements. This is again EGFP, monomeric EGFP in solution. Here is our 2D histogram. Again, brightness versus intensity. And again, you can see that the center of mass of this cloud containing all of our image pixels is a bit above 1, with the difference between 1 and this average being the brightness of our green fluorescent protein monomer. Of course, we have noise, and so it's a little bit of a cloud, and yeah, there's some uncertainty in the measurement. But on average, you can very accurately get the brightness of the EGFP monomer. Okay, so what happens if we plot the brightness versus laser intensity? Of course, if you increase the laser intensity, you will get more fluorescent photons per molecule, as expected. So again, if you do the measurement, put on your cells and find a good laser setting where you can get a decent signal from your cells, but then keep it at that. Because if you change it, your data will not be comparable. The same is true for the gain of your photomultiplier. If you choose that, you will get different values for different measurements, and you can no longer compare them. So you have to be sure to keep all those parameters consistent during the measurement. Here, just as a control, what happens if we increase the concentration of the EGFP solution? As expected, the observed number with that we get with the number and brightness method also goes up. And as we increase the concentration, the brightness stays constant, again, as expected. If we just increase the number of molecules, we don't increase the brightness that we measure. Okay, this all works very nicely for true photon counting systems, but what about systems that are working in the analog mode? So we have to have additional considerations with analog detection systems. So one is that we record the digital levels instead of photon counts. So if one photon arrives at the detector, this can give us whatever 10 digital levels or something, or maybe 20 digital levels. So there's some conversion factor there that we have to determine. In addition to that, there's often an offset. So even if you have no photons coming on your detector, you still are getting some digital values. And then in addition, we have noise because of the amplifier of the detector, especially at low currents. Okay, so we have these 3 parameters that we have to determine: the offset, the analog offset, and this S factor, which converts digital levels to photon counts. And then we have to consider also the variance or the noise of our analog detector. Yeah, and then once we do all these, we measure all these parameters, we can enter them in the software and correct all of these to get an accurate result. So here, just to show you what does a typical analog detector response look like. So this is a histogram of the digital levels that we find in all the pixels. And you see we have, first of all, we have this offset here. So it doesn't start at 0. So this red dotted line corresponds to the detector offset. Then we have this peak here, this kind of Gaussian distribution, which is our amplifier noise. And then we have this exponential decay here. The y-axis is a logarithmic scale, so this is why it's a line here. Corresponds to an exponential. And depending on the slope will describe this conversion factor from photon counts to digital levels. So you can measure basically the dark from your detector and then go in this calibration page where you can determine all these 3 parameters that you can then use in your number and brightness analysis. You'll see that on Friday. Here, just to show you in comparison, this is a photon counting detector. And here you can see that the occurrence of pixels that we get with 0 counts, if we have 0 intensity, so no sample on and no laser on. Almost all of them are 0. We have very few. Again, this is a logarithmic scale, so in this case we have 1 million that are 0, and then only maybe 150 that are 1, and then just a couple of pixels higher than that. So this is, if you have a true photon counting system, this is very nice because you don't have to deal with these additional parameters to correct for your detector and electronics. Okay, here is an example of a 20 nanomolar EGFP in solution. Again, we measure the apparent brightness while increasing the laser power, so perfectly linear behavior if you don't saturate the detector. And the same is true for the number of molecules. As we increase the laser power, it stays the same because the measured intensity only increases. Sorry, the number of molecules does not increase. We only increase the signal because we increase the laser power. So if you do all these corrections, the recovery of relative values is very good in the analog system. For absolute values, you have to be a little bit more careful. So maybe do a calibration measurement where you know the concentration of your solution to get an idea. But anyway, often in cells, you're interested more in relative changes. So did it double, did it triple, did it quadruple? And for this, it typically works very well. So here's an example of a cell. And in this case, it's just expressing the green fluorescent protein, which is not expected to form aggregates. But you can see we have if you just look at the intensity image, we have a gradient of the average intensity, because in this case, we just happen to have more molecules here towards the inside of the cell than on the periphery. So if we plot the map of the number of molecules, we can see this gradient in the concentration. If we map the molecular brightness of the molecules, you see it's uniform. It's the same everywhere because this EGFP did not aggregate in the cell. It's uniform throughout the cell. Okay, so what can you study with this method? Again, we are looking at the focal adhesions, the paxillin molecules. and specifically during migration where these adhesions assemble and disassemble. So the hypothesis is that adhesions mature by increased associations, which leads to these aggregation of molecules and protein density around the adhesions that form. So how can we quantify this? Well, we can use the number and brightness method. Yeah, again, if we have many dim molecules, we should get less strong fluctuations than we have fewer bright aggregates, provided those aggregates still move. So here is an image of a cell expressing EGFP pexillin. You can clearly see those focal adhesions where you have very high intensities. So this is the average intensity map on the left. And then we have the brightness map on the right. And you see we have kind of lower brightness values, so indicating monomers here in the cytoplasm. And then we have some high brightness kind of near the adhesions. Okay, let's go to this data in a little bit more detail. So here we have our NMB plot again. So apparent brightness on the y-axis, intensity on the x-axis. Here with this this kind of pink rectangle, we select a monomer. So this is the brightness slightly above 1 that corresponds to the EGFP monomer for this measurement. And if we select those pixels and highlight them in the image, you see all those pixels come from the cytoplasm area. Now here in the bottom row, instead of the monomers, we only select pixels that have a very high variance, so very high brightness values. And if we map those back to the image, you see that regions around the adhesions gets highlighted. But interestingly, it's not necessarily on top of the adhesions. It's often more around the adhesions. And the reason is once the molecules get incorporated in those focal adhesions, then those molecules cannot move anymore, which means they become invisible to the number and brightness method. They just become this apparent brightness of 1 as an immobile fraction. But these larger clusters, while they integrate, they still move. And this is why we find these high variances near or around these adhesions and only as they form or disassemble. So for example, when the cell moves. Yeah. You can also look at the histogram where you have these different populations of the brightness. Here, fitted with the green curve is the monomer, and then we have the higher brightness ones, which corresponds to these larger aggregates. And we can estimate the average cluster size from this. And for this measurement, it turns out to be about 8 pexillin molecules that are in these clusters that then assemble into this bigger adhesion complex. You can also do time sequence, which is very interesting. So, for example, here we recorded 500 frames and split them up into smaller chunks of 100 frames that we analyzed individually. And then, for example, in the first 100 frames, you can see we have these high brightness values, so lots of these complexes that have formed, and then with ongoing time, these larger aggregates start to disappear. Or they were integrated now into the focal adhesion. You can also see that as a function of time, the average count rate was going down in this case. Then it's constant here while the formation has completed. And here it was going up again as the cell was migrating. Okay, so to summarize, the number and brightness analysis can distinguish between the number of molecules and the molecular brightness or the aggregation state in the same pixel. So here we really get a pixel resolution map. The acquisition of number and brightness data or data for NMB analysis can be done on laser scanning microscopes. You can use the same data you acquired for RIGs, but you can also use camera data with the caveat that I mentioned earlier, which was that you have to make sure your exposures are very short, or you just flash the light to make it very short. Immobile fractions can be separated out because they have the apparent brightness value equal to 1. And I've shown you that the number and brightness analysis of Paxillin was showing that we have this clustering of molecules before they form these larger adhesion complexes. One thing I wanted to point out in the RIGs experiment, we were selecting a smaller pixel size to be able to fit the correlation function. In the number and brightness, we are not doing a fit. We're analyzing each pixel individually, just doing statistics. So you don't have this constraint for the pixel size. So if you're doing a measurement where you don't want to do RIGs, you're not interested in the dynamics, you're only interested in the number and brightness, you can select, if you want, you can select a larger pixel size to maybe be able to image the whole cell and not just a small region of interest. But then you cannot analyze this data with RIGs. Of course, I wouldn't make the pixel size too large, because then, of course, you lose spatial resolution and lose detail of your measurement. So often for measurements, if you have a pixel size that's kind of around the size of the point split function, yeah. If you want more detail, you can zoom in a little bit more. But again, for the RIGs experiment, for the number and brightness experiment, you're flexible in the pixel size. But then again, remember, for the number and brightness experiment, you're not flexible in terms of setting of your laser power, PMT gain, and other things that may change the signal on your detector. You sort it out in the beginning of the experiment, and then you stick with your settings throughout the entire experiment and do your calibration based on that. Okay, again, with that, I want to thank everybody who has contributed to the data that you have seen to the talk, and if there are any questions.
Thank you very much, Nick. Thank you for the 2 talks in a row that you give. Well, I don't know if there are, well, we have time for 1 question. If not, we can meanwhile change to Enrico. There is here in the Ignacio say that he has a question he wanna say.
Ernesto también. Ernesto.
Yeah. Well, Ignacio question say, when you have a family of different species, monomeric and oligomeric molecules, is there a criteria for selecting the oligomeric box wide in the 2D histogram over the brightness versus histogram? And so select only one specific species, for example.
If we do the practical, there's actually a very nice feature in the SimFCS software. So if you measure, if you do a control measurement to get the brightness of your monomer, you can enter that and then just click all the boxes for higher aggregates, and it will automatically put all the boxes and highlight the aggregates in different colors. Yeah.
Great. Thank you, Nick.
I thought the question is on the same pixel.
On the same pixel,
No, you cannot do it.
that is tricky because the brighter stuff will dominate because it will dominate the fluctuations.
Maybe you can mention the PCOMB technique.
But yeah, Liz, Hinde, together with Enrico, they have developed the PCOM, which is a variation of this method, and more advanced, where you can actually separate them out again.
On the same pixel.
On the same pixel, yeah.
Great, thank you, Nick. So now, Enrico, we can move on to your next talk.
But there were other questions. I don't know if you want to answer.
Well, we will have time during the breakout room.
Okay, whatever.
We'll do that during this section, so we can stick with the agenda.
Okay.
Thanks, Nick, very much. Well, the next talk is by Enrico. I already introduced Enrico. For those of you that didn't have the chance to listen to my introduction, I will only say that he is professor at the University of California, Department of Biomedical Engineering, and the PI of the Laboratory for Forest Dynamics. And in this talk, he will talk about a particular technique, which is very nice, and is intended to find the path of a single molecule, as I said before. And he will, I think, address how we are sure that this is exactly the same molecule that we are speaking.
Okay, well, thank you, Lionel, very much. And so let us see if I can enlarge my screen. And okay, so that should make the screen larger. Okay, so this technique is called a pair correlation approach. And pair correlation as a word or as a term has been used very much, for example, in a liquid to look at the alignment of dipoles or water molecules, whatever, one with respect to the other. Here, the pair correlation terms is used in terms of spatial distribution, as I will show in a moment. So the pair is considering 2 points at a given distance. So first of all, in order to introduce this concept, I want to summarize briefly what FCS is and have a very short history of FCS. Then I will talk about the pair correlation concept in one dimension and detection and localization of barriers to diffusion, application to nucleoplasmatic shattering, and then I will talk very briefly about in 2-dimension and 3-dimension. Okay, so first of all, let us start with the brief history and what that means. So we say that fluorescence correlation spectroscopy was first described by Doug Magde, Elliot Elsion, and Watt Webb, and in papers dealing with reactive system, and was intended to be for looking at the speed of rate of chemical reaction. So in that paper, well, it's not strangely enough, but given the time, everything was discussed as changes in concentration. So the term molecule was never used, although they were observing, as I tried to explain in my previous presentation, a single molecule, but it was never used. Instead, the particle interpretation, so that we are measuring particles, single particle in FCS, appeared later on, or more or less at the same time, and was the work of Rudolf Rigler and Manfred Eigen. They didn't make a big issue about it, but simply all their derivation and their paper talk about single particle, which is a very important concept. However, we still need one more thing, and the question is the observation of fluctuation from the same molecule. So how do we know, in the description I have, until now, we will describe, or I describe, how the fluctuation in intensity is caused by one molecule leaving and exiting the excitation volume. But how can we know if it's the same molecule or is another molecule? And that concept has been discussed in the literature in many different papers. And I quote here Zeno Folder's paper, who has a paper in 2001 in Biophysical Journal. And I think I am the only one ever read this paper. But this concept is very important, as you will see. And the use of the spatial correlation in FCS, so dynamic correlation, was developed, I would say, recently by my work with Michel in RIX and MB and other things. But still, there is a concept which is lacking. So let us see what is that part. And generally, the concept of looking for a particle moving in a cell or in solution or in a surface is done using single particle tracking. And again, the term single particle tracking means that you have one particle only in the field of view or more, but they are well separated one from the other, and you simply measure the coordinate of that particle as a function of time. This is not possible if you have many particles in the field of view. Okay, so let us see how we proceed from that. Okay, so the idea is, can we join this detailed description of single particle tracking, which gives information about the trajectory of the particle, but using many molecules? So let us see how we can do that. So first of all, there is a precedent of what we have done in looking fluctuation spectroscopy for flow. So you have, as I have described, a volume of excitation, and you have a particle moving through the molecules of excitation. So when it's in or out, you will change the total fluorescence, and so you will determine to the correlation function how this can change. There was a question in the chat about why I have -1. Well, the -1 is every time you use here the fluorescence, total fluorescence, you will get a -1. If you use the change in fluorescence, then that -1 disappears. It's simply a question of definition, okay? So it's nothing important, it's not an error, and it's not. So here I use the total fluorescence, so I use -1. If I use the delta F, so the change in fluorescence, that -1 disappears. Okay, so that is the simple explanation of this effect. Okay, so there is a paper in which people try to measure not using only one point, but using 2 points. So they were, for example, a particle which gives a fluctuation at this point, can give or not a fluctuation in the second foci, so in the second volume of excitation. So that was worked out, and the correlation function that determines was used to measure flow, it came out to be an exponent, a Gaussian rather than the polynomial terms that we were using. Okay. So now let us talk about this pair correlation concept, where it comes from and how we can perform single measurement in a sea of many particles. So the idea is the following. So we have to change language a little bit, and let us consider the following model. So suppose we have a grid of points that you can associate with the camera, but doesn't matter. And you can measure the fluctuation at point 1, the fluctuation at point 2, the fluctuation at point 3, and fluctuation at point 4, and repeat for every point in the measurement, in the image. Now the question is, suppose we have a barrier which is indicated by this blue line, which the molecules cannot pass through. So the question is that if you have a fluctuation in position 1, might be yes or might be not, you can measure the fluctuation in position 2. But if you have a fluctuation of a particle passing in through, and you have a barrier, will never reach point 3. So that will be a lack of a correlation between point 2 and point 3. Then point 3 can correlate with point 4 at some later time, but essentially a barrier divides the space, well, in this case a plane, in 2 regions. Regions which are connected here and regions which are connected in the other side. But no one particle in this model can pass from one part to the other. This is a very important concept. Okay, so let's go to the second concept that we need to use. suppose that instead of a barrier, which is impenetrable barrier, we will have an object. Simply, the object is impenetrable, but there is not a barrier. So if you have a fluctuation in a point, for example, here, the fluctuation, that particle can be found in the other side, but have to go around the object. And the particle here can be in this side or can be in the other side, but will appear in the other side with a time that depends on the path following by the molecule. So the two cases are, in one case, you can never cross the barrier by construction. In this case, you could, but you will have a delay in going around. So those are the two cases that we will consider. And now let us be more analytic and see how we can do that. So now, if we can correlate in time, in a grid, in time, all the fluctuation which occurs at different spatial position, eventually we can measure the time for a particle that was in one point to reach the other, but not, for example, to pass through this barrier. And here, what we will have is a change which is longer, so it will take a longer time to appear in the other side. So let us see if we can make things more analytical. Okay, so here we have in this variable log of time, and this in this axis I have positions. So suppose you have a time t equal to 0, a particle in this position. Due to diffusion, it will appear with a square of time in a parabola which is represent all the points that can be reached by a particle diffusing, for example, freely in solution. So if I am correlating point 0 with the point which is here, at a very short time, it will always be 0, because simply if a particle is here, cannot be there, the same particle. But if I wait enough time, so if we wait enough time, eventually that particle can reach a different position. So this is the concept. And now let us see how can we make this concept more analytical. So in this graph, I plot not really the correlation function. It looks like a correlation function, but I plot the product of the intensity of a point or the point at a given distance. So if the points have a very small distance, I will get some correlation, even at very short time. If a point is at the long distance, I will never get a correlation. So I have to be 0, or actually, as we will see in a minute, will be below 0. So that is not really a correlation function. That is the product of the intensity at one point, 0, with all the points which are at the given line. And essentially, you will see at in a very far point a correlation, but you have to wait for a given amount of time for that particle to appear in a given position. Okay, so this is what it is. Okay, let us see how we will analyze. So for the moment, let us concentrate on the simple concept that we can measure the intensity along a line. And so those are points in a line. And how will that appear? So if I plot that position here, that position in a second point, so I plot what is called the carpet, so that each position along a line is plotted in this axis, and then as a function of time is plotted in this axis. And then I say, well, maybe you can see that there are some fluctuation that propagates along a diagonal, which is very likely to be the same molecule that simply is moving in this direction. So let us consider the following concept. So I measure the fluctuation, for example, in this position, which I call R equal to 0 because it's at the center. And then I measure the fluctuations at a given distance. And then I do the pair correlation. So I do the cross correlation of the intensity at this point with respect to the other point. Well, at very brief period of time, I will get nothing, because I have to wait the minimum amount of time for the particle to appear at a given distance. So in this case, I have a correlation function, which is more complicated than I did in the past, in which I have a correlation function which will depend on time, so the time to respect to this time, but will also depend on the distance. Will depend on how far is one point to respect to the other. And this is what we call the pair correlation function. Again, I have one because I use f instead of delta f. Okay. So now, why I said that in this method I will only see the same particle, and let us see what it is. So why? So for example, suppose at time t equal to 0, I have a particle in this position. Well, there could be some fluctuation in the other position due to another particle. Okay, and I can correlate that. But if I continue to correlate those particles, so sometimes I will see a particle here, but sometimes I will not see a particle there. So if every time that I see a particle in this position will also be found in a different position at a different position and at a different time, that can only be the same particle, because only the same particle will correlate with itself, but never with something which is different. The difference, if it's a different particle, will contribute to the total part in the denominator, but will not influence the correlation function, which comes from what happens in the numerator. So, say that, let us do a simulation to show if my idea is correct. So here I simulate one particle, here I simulate two, here I simulate three, and so on. So if I have only one particle, can only be correlated with itself. If I have more than one particle, well, I will have different times. So let us see what is happening. So if I do the correlation function of one particle, two or three or many, I obtain always the same result. And the same result is the following. So if I correlate at a distance of, for example, 1 pixel, because I need to index by 1 pixel and as a function of time, I will obtain now what is called a pair correlation function, which will be that blue line. And then as I go farther and farther and farther, at the beginning, I will have no correlation, and then only when the particle will appear at that coordinate, I will have some correlation. Of course, the intensity and the probability will go down because I'm only analyzing a line. So if I will analyze a space, it will be different, and I will discuss that in a minute. So when the distance between the 2 points is small, points are within the same volume of illumination, which produce a correlation of intensity at a very short time. But when the distance increases, I will have a correlation only if the same particle is found with a certain delay at a different pixel. So this is very important, and let us analyze now those correlation functions more in detail. So first of all, here I plot the correlation function for different diffusion constants. For example, a diffusion coefficient of 0.2. So if it's slow, the particle will be found at some point. So this is the pair correlation at a distance of 10 points after a long period of time. I have to wait for the particle to be there. But if I consider, for example, a particle moving very fast, like 10 micrometers squared per second, they will appear earlier. So you can see the green and the blue curve will appear at different time, and not only at different time, but will appear also in this graph almost of the same width. So the width of this line is almost independent on the diffusion constant, will depend on the dimensionality of the space, but the maximum will appear at a very different time. Now suppose we have a particle that can diffuse, for example, with a time of 10 micrometers squared per second and 0.2. Well, I will have two peaks. So the particles that are fast will appear earlier, and the particles which are slower will appear later on. So I can separate all the particles on the basis of when the peak will appear. So now you can see that the amplitude here decreases. So if I go very, very large in correlation time, it will be very, very low there. So how that changes? Okay, now follow this drawing, and I will try to explain in detail because it will be important for the two-dimensional case. So I have a particle which is measured here, and that gray surface indicates the point spread function. Okay, so the particle is moving, and I scan the line in this direction. So two things can happen. Either that the particle leave the area by a path which will be not passing through this point, which is the point I am measuring, or will pass through that point. Okay, so let us see how many particles I will measure. I will measure a particle that will be the ratio of how big is the point spread function with respect to the length of the circumference. And if you look like that, that means that the probability here will depend on that ratio. So particles will leave different regions, but I will miss them. But in 2 dimensions, for example, I should be able to measure all of them. Okay, so that will be important later on. Okay, now let us see. Until now, I did only simulation to see if the software works okay. Now let us do a real experiment. So this is bits which are just freely diffusion in solution. And I calculate the per correlation function. What I calculate is that if I go to PCF of 1, so at a very small distance, where is the same thing that measuring the autocorrelation function. But if I go to a very large distance, I will have 0 or very low probability here, but high probability at a later time, because it will take some time for the particle to reach that reach. So this is really the principle. And now let us see how I will be able to see if the space is connected or the space is disconnected. Okay, so let us suppose that the space is disconnected, so we have an impenetrable barrier. So a particle at 2 can never be found at 3. So that means that if I paint the image on the basis of that probability, I will have lines which are dark because we never reach that region. But if the particle can go around a given structure, it will take longer time. And the longer time will appear as a connection, as a semicircle, so that at a given time, there will be a connection between the parts, but the connection will be delayed. So that connection will disappear, so will be longer and longer and longer if there is no connectivity. So the rule is very simple. If I see a black connection between 2 points, that means there is never a particle from one side to go to the other. And that means no communication. If I have a delayed communication, that means that I'm passing through reaching the same point, but after some time. Okay, so I will talk more in detail about nuclear pore complex and so on. But let us see for this very simple experiment how we'll do so. In nuclear pore complex is the following thing. So there is a structure. There are many of those a protein complex in the nuclear envelope. So this is a nuclear envelope, so that is the cytoplasm, and that is the nucleus. And well, there are many things here, but the more important thing is to concentrate on the size. So a nuclear pore complex is about, so first of all, is a octamer, so it contains 8 equal units, and allows the passage of molecules through the nuclear pore complex. How the molecules will pass through the nuclear pore complex is part of my application, and I will discuss more or less later on. But what is important is that the nuclear membrane is like this is a bilayer, and this is a double bilayer, and there are proteins in the middle, and then eventually connect to the ion. Okay, so the question is, can molecules pass through the nuclear pore complex just by diffusion, or we need an active mechanism? And the diffusion, the active mechanism will be measured by, if I choose 1 point here and 1 point there, that will be diffusion. But if I choose 1 point here and 1 point there, eventually I have to be able to tell if it's diffusion or it's active channel. If I choose 1 point here and 1 point there, well, it will be diffusion in the cytoplasm. So I can separate the diffusion in the cytoplasm, the diffusion in the nucleus, but also what is happening through a nuclear pore complex. So let us see if we can do that. So clearly, the passive diffusion will be bidirectional. So if it's passive, it's simply diffusion. Will be, we know that it's regulated by molecular size. So everything which is larger by 60 to 70 kilodalton will not pass through a nuclear pore complex by passive mechanism. And then will be energy independent in the sense that you don't need any, it's just diffusion, so it's temperature, is determined by the temperature. If we have active transport, then it will be very different because, first of all, the active transport can be unidirectional. So molecules will pass from the cytoplasm to the nucleoplasm, but not vice versa. Will be driven by specific amino acid in the proteins here, which form what is called a nuclear localization signal or nuclear export signal. So some molecules will be transported in one direction and some molecules in the other direction. It's generally not affected very much by molecular size, but it's energy dependent because in order to pass something by active transport, you need some energy, source of energy. Okay, so this is the kind of experiment we have done. So we have the cytoplasm, we have the nucleus, and we have nuclear pore complex, and there are many in the nucleus. Now we have a protein, which is GFP, in which we added a nuclear localization signal. That protein will form a complex with importin alpha, okay? So that complex of two proteins will form another complex with importin beta, and the entire system, exp minimum, we will need in order to pass through the nuclear pore complex by by active transport. Of course, if there is no NLS, things can pass through non-active transport. Okay, so let us see how we do the following thing. So this is the triplet, the complex, and will pass through. Okay, when it passes through, depending on the concentration of another protein, the RAN-GTP, the complex will disassemble. And once it disassembles, will not pass back again. So all the active transport is dominated by the relative concentration of GTP between one region. So RAN-GTP will be very concentrated in this place. Of course, if the complex will not form, it will just disassemble. So the gradient of RAN-GTP exists, and this can be demonstrated by several things. And actually, the cells spend a lot of energy in order to create that gradient. Okay, so essentially, molecules can go, I say, by inactive transport or passive transport. Okay, so let us see. Experiments were done, with different proteins and different size, and a simple GFP should pass also by active transport, by passive transport. Okay, so those are experiments done by other people and shows that more or less what is supposed to be the nuclear envelope, a molecule arriving there, and then eventually passing through, and that can be done by several experiments. Okay, so essentially what is happening will be to follow in the standard method requires to follow a single particle and measure how it changes position as a function of time. Okay, so let us see if we can do the same thing by the pair correlation function. And I describe here the experiment. So we have a molecule, GFP, that has a nuclear localization signal, so will concentrate in the nucleus. So the nucleus will have more, and in the cytoplasm we have less. And then we will draw a line in this direction between the nucleus and the cytoplasm. And then we will follow, we will calculate the pair correlation function or autocorrelation function every point along this line and see what happens if we get the point here, and then what happens through the nuclear envelope and so on. Okay, so in the line, we do a line very fast, and you will see why that is needed. So the line is not very long, it's 32 points long, but we can measure each point is about 100 nanometers. We need that sort of resolution. And each point is measured in less than a millisecond. And that also is essential for this experiment. So the size of the PSF is about 200 nanometers, as we realized. So that will be more or less the size of the PSF. So we move the PSF in this direction indicated by the arrow. Okay, so as I said, between one point and the next point, it takes only 6.3 microseconds. So it's very fast. So general molecules will not move so fast, well, in that size. So we will show the time it takes to go from one point to another along that line. So a line is repeated every half a millisecond approximately. And so we will have a point at very high rate and lines at relatively large rate, but always lower than a microsecond. If you don't do that, you will not see anything. So now let us do the carpet. So we are going point along the line. And so that will be the nucleus, more intense, the cytoplasm, and that is what we define as the nuclear envelope. Okay, so let us do the autocorrelation analysis. So the autocorrelation analysis shows that there is more particles or less size of the correlation function in the nucleus because we have more concentration, and here there is less concentration, but there is, this is the autocorrelation, so it's a point with itself. Okay, sorry, I went to the end. I didn't intend to go to the end. Oops. Oh well. I jump out of the, okay. Okay, so we were here. Okay, oops. I don't know why we jumped to that. Oh well. So let us see if otherwise to advance will be better. Okay, so we discussed that, we show that. Okay, we showed this one, and look at the time it takes. So in the, remember that that part is the nucleus. So in the nucleus, molecules move, this molecule GFP move faster, so has a diffusion coefficient of 11.6 micrometers squared per second, and the cytoplasm moves slower. That's a fact of this part. But now, if we plot every single of those curves, we see that there is one curve which is at the nuclear envelope, which is very different than the others. And that curve implies that something happens at the nuclear envelope. And so this is the nuclear envelope, and it shows that actually at the nuclear envelope, it takes longer to pass through because it's a diffusion through a narrow channel. And so if we continue like that, so we can see that intra-compartment, nucleus to nucleus, we can measure very well the correlation there. Now if we do the correlation function, we can see that if we measure from one point to another point, in the same compartment, we can obtain the pair correlation of 1, the pair correlation, and then when we arrive at a large distance, or a relatively large distance, we start to see a total different correlation function, which means that the particle that was here was not there, okay, and appears at a time which is long. And then, so we measure between cytoplasm and nucleus, so passing through the nuclear envelope, and now we can start to see that arc I was talking about that indicates that there is a correlation, a much longer time. This is about 150 milliseconds. And the particle takes 150 milliseconds by diffusion to go from one point to another. And then finally, we can measure, so this is still the part of the arc, what happens when we are only in the cytoplasm. When we have only in the cytoplasm, well, we see the motion is lower, so we can obtain the diffusion, so it's not the diffusion, the time it takes from one point to reach another, passing through the nuclear probe complex. And when we pass through the nuclear probe complex, we obtain a much longer time, which means by diffusion is it's much longer time. Now, the question is that we have here a series of bumps in this curve. But the point is that the nuclear pore complex are very close one to the other. So it can take a time which is longer to pass to the next one, and it will appear it passed through or the direct one or not. So we have like a series of channels where the particle can pass through. Okay, so let us see what happens if we change the amount of ATP. So ATP is necessary only for the active transfer. Well, with ATP, we see that the GFP goes into the nucleus as it's supposed to go, is for the active channel. Without ATP, it's more or less distributed uniformly as it's supposed to be. Okay, so we can get all this correlation function and show that actually every time we have this arc, which means that it passes through, but it takes some time to pass through. Okay, so under energy, when we deplete energy by controlling the amount of ATP, we get uniform thing. So we delete completely the active transport. Okay, so let me finish with the part now of two-dimensional PCF, which will be used also by other presentation. And in two-dimensional, first of all, we want to know what happens if we have two different cells. So if we have two different cells, clearly, well, the GFP will not jump from one cell to another. So that will be the case control experiment in which we have no transport. And in fact, between cell 1 and cell 2, we have essentially no intensity. Then when we measure the correlation, we have arcs here, arc there, but we have a black line at position 7, which is exactly the time between the cells. So essentially, we can measure the same molecule stay in one side and the other. Let us rapidly do now the two-dimensional pair correlation function. So I say I will have no formulas. I have only drawing because it's much easier to explain with drawing. So in what I said, we were measuring the correlation between one point and another point at the given distance. But what happens if we measure the correlation of that point with that point, with any point around the particle? Eventually, the correlation function will change if the system moves homogeneously. Every direction is the same, will be all the same. But if it's not homogeneous, one direction will be, for example, have higher correlation than the other, okay, or will reach. So let us look at the following thing. So instead of showing each correlation function, which is very difficult to understand, I will show a surface. So in which each one of those curves is showing that. This is, and then I have 32 points because I decided, or 36, I don't remember exactly. So divide the angle in essentially position of 10 degrees. So every 10 degrees, I measure the correlation between this point and the point at the given distance. Now, if the barrier of diffusion is very far, that distribution will be essentially round. But if I start to draw, to put a barrier which is close, all the direction, this direction will not appear in the correlation function because the particle cannot correlate from one side to another. So the correlation function drawing this angular representation will have a shape which is different than the other one. And what is nice is that the change in shape will occur in the direction of the position of the barrier. So if I look at this shape and I plot this shape, I will be able to tell not only if the diffusion is free in all directions, but where is the barrier? Okay, so will also give me the direction of the barrier. And this is what we will do. So first of all, I need to be careful about the following thing. So suppose we have a barrier or a region which is inside a barrier and and the other region which is outside. But the number of molecules is the same in my simulation. So coming from this side, I will see at some point the deformation of the shape of the two-dimensional shape of the point spread function, of the percorrelation function, but will be identical in both sides. So a barrier will give two identical regions, and then I can draw the direction of the deformation, and I paint in color the direction of information, and then I say, I have a barrier here, has that direction, then I draw a line which indicates that particles will move more favorable in that direction rather than cross. Simply cannot cross because of the construction I have. So this color, so the deformation and the color of the deformation will give me the direction of the motion. So suppose I have a channel. So in a channel in which particles can move and the other parts too, I will have three parts. This part, which have molecules which have one side and cannot penetrate into the channel. Here, molecules that can move into the channel, and here, exactly like the same before. So if I draw the direction of the particle, I will end up with what we call the connectivity map, which says molecules will move in this direction, molecules will move in this direction, will move in the other direction, but they cannot cross. So I will have that black line and that black line. So this is the result that I expect to be. So now suppose we have more complicated shape. So for example, I have a circular barrier. Well, a circular barrier, that means a particle cannot pass the barrier, so they will give a correlation function which is higher in this direction, higher in the other direction, and now the direction will be horizontal, vertical, depending on where we are. And if I paint that in the form of connectivity map, I will obtain directly where the molecules move. And of course, I can do more complicated things, or that will be a square region. And if I have a cross, because now in a cross particle can move in both directions, I will have a connectivity map of that side. So you can see that the connectivity map tells me where the barriers are, and that the barriers are impenetrable because I count, the number. So that would be an impenetrable barrier, and so on. So I can do all this kind of calculation. Let us do things which are more complex. So I have a cell, for example, that has regions which are essentially bound by a barrier. So the molecules can move in that yellow region, but can never penetrate in the red region. So if I measure the connectivity, so in the yellow region will always move, and they're all connected, but they are not connected with the interior part because simply they cannot move and go to the barrier. So you can see that I have here a geometrical shape which is very complicated, but using this method I can unscramble the shape in a very easy way and tell you exactly where the particles are moving. And this is an experiment that we've done in cells. So for example, this is NIH treated 3 cells, and I have, this is, I think, the entire cell, this is the nucleus of the cell, and this is a nucleus in the cell, and you can see that the molecules in one part can move here, can move there, but only few penetrate into the nucleus. And yes, there is some way to penetrate into the nucleus, but that happens very infrequently in comparison to the other thing. So in summary, the percorrelation method measures molecular flow at the 100 nanometer scale. So those simulations were done with regions of 100 nanometer apart one to the other. Experiment with beads reproduced a prediction. So the maximum of the correlation function will occur after some time. I didn't explain very much how come I get negative correlation times. I will explain that if you have any question. The simulation showed that we should be able to detect diffusion boundaries that are below the resolution. Experiment with the molecules in cells show obvious barrier to diffusion at the junction between cells, as I show. experiment using the EGFB with NLS showed passive and active transport to the nuclear pore complex, and diffusion of molecules showed disconnected region of flow. A connectivity depends on the cell cycle. I have not shown that, but I will have some more information in the application. I will show this later this afternoon. Okay, I think I will stop here, and I will answer your questions if you have any.
Right, thank you, Enrico. There is a question here in the chat. I can read it for you.
Yes.
It's in Spanish, and I will translate both way. The question is how I can characterize the noise with the part correlation function, and if there are any maximum value in the correlation that we can do or not. I mean.
Well, okay. So when you show the correlation, you show not one but many points. So this is like a two-dimensional correlation. Well, yes, you can have some noise. In fact, if you measure here and here and here, you see it's not exactly circular it's supposed to be. So those are the actual correlation function that are measured. So each correlation function has some noise. And the noise is determined just by normal kind of noise, which depends simply on the statistics that you have. So more photons you have, the better you measure, and so on. So if you want to look at the other thing I show in the other data, not simulation, but data, for example, here, the previous one. Okay.
The other point, Enrico, is I mean, when you are cross-correlating two points, noise it will never be cross-correlated. So the noise will.
Well, yes. So
right?
essentially, I look at black lines because there is no connectivity.
Exactly.
Or lines which have circles. So the circle are not perfectly defined, but circle means you have to go around. It's so easy. And black means you don't pass. So black is black in the graphs I show. And that might be you have an error a little bit. So, but it's on the time, and it's not particularly large. Okay. I didn't discuss the negative source. And the negative source of the correlation function is very important. So the fact that you go negative that means that the particle which is in one position cannot be in the other. So you see all those curves have a negative part simply because the particle, you are at a distance that the particle cannot be measured. So that means, like in this graph, okay, so that means that the particle is here, cannot be there. Okay, so it's a anti-bunching, special anti-bunching.
Yeah. So we will assign the people to the breakout room, and we will have more or less like a 10-20 minute break. And then
have you decided? So Laura apparently is not feeling well, and she will not be able to give a talk.
We will have a little change in the agenda. Unfortunately, Laura Estrada is sick, is not feeling well, and basically after Susana, Enrico is gonna fill the gap between Laura and him. He will talk.
And I have prepared another presentation which is about what happens in the nuclear pore complex.
Perfect. So while we are preparing the breakout room, are we ready there?
Yes.
There is a new one thing.
Okay, so let us see. But the breakout rooms are now or will be in a few minutes?
We are now.
It's 11 o'clock now, my time.
Yeah, we are now assigning the rooms and changing the.
Hola, Susana. Estás muted. No te puedo oír. Estás muted, no te oigo.
You're now muting?
Give me a second, I will.
Okay, so I will go in room 2.
Pueden desbloquear a mute Susana porque está bloqueada. No sé. Give me a second, Susana. We are just handling with the breakout rooms. I think now you are able
Hola,
to... Hola, Susana.
Susana,
¿cómo están? ¿Qué tal?
Muy bien, muy bien.
see you.
Hi,
Try-
Dave.
Trying to deal with all these things of Zoom and everything, you know.
Leo, entonces a las 4:15.
Sí, sí. We make a mistake with the breakout room, so they will come back and we will assign again.
Stay in a room. Hola.
The general thing. Anna, how do you like my Aloha shirt? Sandy made me wear one today.
I cannot see completely.
Well, I have on an Aloha
Can you
shirt.
stand up? Can you stand up?
Well, I'll move back.
Yeah, do some modeling. Beautiful.
Don't worry, because she made me pick out to wear a different Aloha shirt every day I talk. So,
Excellent. So I will keep my eyes on.
yes, okay. So you can tell her later if you like them.
Okay, sorry, guys, we make a mistake. We will do it again. Just a second.
Why you don't just do one big room?
I think it's easy
For them?
to split.
Yeah, 43 people, Anna, so.
Oh. Hola, Enrico. Estás mudo. Enrico, you're mute.
Okay.
Ahora sí. ¿Qué tal?
Okay, now you have to join all again to the breakout room and you will be...
Okay, so because I already was there, so join.
I know, but we canceled by mistake.
Ujú. Bueno, yo 4:15, entonces me aparezco de nuevo, Leo.
Perfecto, Susana.
Estoy aquí, digamos, si quieres antes también.
And they are going or not? Creo que sí. Well, for the rest of the people that we are still connected, if there are any other questions or if you want to discuss anything regarding to the previous talk, or I am more than happy to spend this time with any of you.